Uh, let there be some more co-hosts so that they'll be helping the host. Okay, I think it is 10:12 and we are 60, 64, 65. Okay. So shall we start? If you have any suggestions, we'll spend 5 to 10 minutes on that. Later, we'll have some activity before we invite Walter. So if any of the group members have anything to share. Okay, can you all hear me actually? When I don't get
Yes,
any.
sir.
Yes, sir.
Okay.
Yeah. Very nice.
Okay, okay, great. So, okay. So we have a small quiz for you all. Okay. I'll request Shivakoti. I think 30 seconds for each question should be fine, or it's a easy, simple, multiple choice questions. There are three or four questions. So those questions will appear on your screens and you have to select one correct answer. Okay. So I think Shiva, please take over. And how much time is required for each question? I think 1 minute should be fine, I think. Okay. Shiva, please carry on.
Okay, sir. Okay, sir.
So one after the other it is coming. So total 5 minutes or something. Can you all see the questions on your screen? Hemabindu, can you see?
Yes, sir. You can see the questions.
Okay.
We have 67 participants with us, and till now only 10 have answered the questions. So I would request you to answer. Till now, 27 of you have answered the question. We are waiting for more people to respond. Uh, 43 people have answered the questions. We will wait for 2 more minutes and then we'll close the poll. Remaining participants, I would request you to answer the polls. Only 42 of you have answered till now.
Only 44 have answered. Others, please hurry up. Hope you all can see the questions on your screen. Otherwise, let us know.
If you click on the polls tab, you'll get the questions as well. We will close the polls responses in 1 minute. So if you have not answered, please answer. It's a learning exercise. So even if you are wrong, it's okay. But it's very important to participate and answer.
Yeah, only 52 have answered, right?
Yes, sir.
So someone is sharing the results.
Yes,
Should we
so
discuss the
Shiva will be
result?
sharing.
Yeah. What does the group say? You want to
So I will.
see
Yeah,
So I,
share.
the result? Yes. So first question, role of plant root exudates. In how many different ways uh, plant root exudates serve purposes? So which is correct? So 10% of the group said maintain and support a highly specific diversity of plants.
Dharmender sir, you're not audible. Also, I'll continue with that. So first one is role of plant exudates. First option was protect plant roots from harmful microbes. No one answered for that. Maintain and support highly specific diversity of microbes in rhizosphere. Serve as signal to initiate symbiosis with mycorrhiza and rhizobia. And the second last option was all of the above. So that was the correct option, and 85% of you answered as that. Second question was mass of substance divided by volume it occupies, expressed in units, gram per cc, is the definition of. First option was surface area. 17% of you answered as surface area. Second was bulk density, which is the correct answer, and 83% of you answered bulk density. Third question is what is the biggest carbon sink? Soil, forest, oceans. Oceans is the correct answer, and 54% of you answered oceans. Soil, 31% of you answered as soil, but ocean is the biggest carbon sink. Fourth one, transpiration will be maximum under which set of following condition? First, open stomata, dry atmosphere, and moist soil. 40% of you answered that, and that's the correct option.
Yeah,
Second,
Diksha, you
yes,
said the carbon sink, soil is the highest, not oceans, for your information.
sir, actually, oceans is the highest.
No. If excess carbon is there, oceans will absorb, but you can say sequestrate carbon, more carbon. How much carbon you want, you can send it into the soil. That is the main objective. And your answer was soils, but not oceans. You are telling oceans. How? Your
Sir,
answer is soils.
sir, actually, ocean absorbs the most carbon, but we will talk about it later after this conversation ends, like after this call ends. So for the fourth question, the third option is open stomata, high humid atmosphere and dry soil. And the last option is closed stomata, dry atmosphere and dry soil. So these were the four questions for the polls that we conducted. And next module also will be doing the same exercise to refresh your memory. Over to you, Dharmendra sir.
Ma'am, once more, what is the right answer for fourth one?
The first option was the right answer.
Thank you. Thank you.
Walter has joined us, so I'm promoting him to panelist. Good morning, Walter. Can you hear me?
I can hear you, and I'm just starting the video. Hopefully that'll work. Can you see me? You can't see me yet.
I can't see you yet.
Okay. You cannot start your video because the host has disabled it. Okay. So could you please just switch your video on for me?
Yes.
No troubles, all good.
Can you try now, Walter?
Okay, let me try start video. Yes, I am on. Right, very good.
Very nice to see you, Walter.
Yeah, very nice. I'll just close the window because it's reflecting on the sign. It's okay. I'll be right back. I'll just.
I'm back. Can you make me co-host? Sorry, everyone. There was a power interruption and I got out of the meeting.
Right. There you are. That might be better.
Yes, Walter.
Okay, good. Excellent. How's everybody been? Everyone's been well?
We are doing good, Walter. Good morning. Good afternoon.
It's good. Good afternoon. Good afternoon for me. Good morning for you. And yes, no, it's good. We're number module 3 or Q&A on module 3 and working on module 4. So it's progress. It's going well.
Yeah, it's going on well. And we are all doing some assignments also.
I've been
learning together.
Been listening in to you doing your quizzes and your questions. Yes. And that's good. I mean, there's so many wonderful questions are going to come. The last one I heard of course, which was the biggest carbon sink. And obviously the oceans contain 38,000 billion tons of carbon dissolved in them. 38,000 billion tons, 50 times the carbon in the atmosphere. The world's soil contains 3,000 to 4,000 billion tons, which is about 5 tons in the atmosphere. But definitely Diksha was right that the oceans are by far the largest sink, about 10 times the soil. But of course, the other gentleman was saying, well, we can actively manage the soil to increase carbon, whereas of course we can't do that so quickly with the oceans. So from a management point of view, I suppose, yes, there's a valid point. It's soils that is a point of agency where we can influence it, but definitely globally, the oceans are the largest sink. The second largest sink are actually methane hydrates. That's frozen methane in the oceans and also in tundras, in the actual Arctic frozen land in the tundra peats. And there's about 15,000 billion tons of carbon locked up in what we call methane hydrates, and of course locked up in the tundras. And that's again about 4 or 5 times larger than the soil. But again, these things are locked up and have been for hundreds of millions of years. So they're not really manageable sinks. But look, very important questions, very good answers, and of course, very good discussion on detail coming from it. I mean, you guys will have to take over the masterclass soon and run the whole show. And I'll be trying to answer the questions for you if I can. But okay, but that's the whole idea. The whole idea is a masterclass that, yes, that you actually become empowered, but also you become teachers for extending the whole natural farming vision and the natural farming practice throughout India and then, of course, globally. So wonderful. Thank you.
Thank you, Walter. So I think we have some group questions that the groups have given, subgroups have given. I think Diksha will present one question after the other. Diksha, can you please do that?
If
Yes.
I may to interrupt, just sorry, like before, it's probably worthwhile to recap where we are a little bit, what we've been doing so that people are refreshed. And then, yes, Diksha, look, thank you very much. Let's get straight then into the questions. But as you all know, we've been running this masterclass. We're now actually at module 3. Okay, we started off, of course, with an introduction, and then we had the first module, why natural farming is so important for India's food, water security future, and globally. The second module was all about what we need to do, what are the specific practical targets, ecologically, socially, at a farmer level, economically. So, what are the actual targets that we have to work towards at a practical level, very important. And this third module that we're actually having a Q on now is actually how can we achieve this? What are the practical ways of achieving it? And of course, that was based on the module that we sent you for everyone to look at. And really, it's all about good news, right? The good news powerfully is natural farming is unique, the only thing that can actually do this. In a sense, the good news is that nature has solved these problems for us. Okay, nature 420 million years ago on vegetating the global landscape more or less said, yes, how do I do it? And she, in a sense, solved that problem by creating pedogenesis or soil formation and really creating biosystems through creating soils. And as we've been talking, she did that by building soil carbon, mixing organic detritus with the mineral detritus on what had been the arid, dry wasteland, and in that way building soils. And she did that basically, as we've discussed, through microbes, colonizing and solubilizing that rock, breaking it down, and then, of course, enabling plants to grow in that primary soil, and, of course, putting carbon, essentially fixing solar energy and carbon dioxide into sugars, into cellulose, into lignin, into organic matter, which is then the basis of making soils. So it's that exquisite natural process of photosynthesis, of basically solar energy capture, fixation through carbon dioxide, through plant tissue, that has actually created the sponge. And of course, once we created that soil carbon sponge, then in a sense, we have biosystems. We can actually evolve ever more productive biosystems, excuse me. And then those biosystems, of course, have extended right across the 14 billion hectares of ice-free land on this planet. And these same process of pedogenesis, soil sponge formation, nature is used over and over again everywhere on the earth, and every time there's been a massive disruption. So, for example, when you had a big lava outflow in India and formed the Indian Ghats, those big lava fields, nature came and said, how do we regenerate this? And she used that same pedogenesis process to revegetate and turn all that lava flow into very productive, healthy soils. So whether it's glaciation, volcanism, earthquakes, tsunamis, every time there's geological destruction, then of course nature comes back and regenerates through building the sponge. And of course, we are doing exactly the same thing. We're saying, look, here is nature's solutions, and we can use the same tools and accelerate those same processes that nature has to regenerate earth, to regenerate healthy soils, and with that, hydrology, climate stability, food, water security, and of course, stable societies, which is, of course, what we said in the first module is really the critical challenge for humanity. Okay, so it's that simple process of nature, plant growth, pedogenesis, soil formation, and then resilient biosystems. The other issue about how we do it is really powerful, wonderful, because again, it's you in India, East Asia, whether it's China, India, Japan, Korea, who've in a sense demonstrated that, yes, these natural farming systems have enabled populations, hundreds of millions of people to be sustained for thousands of years in cultures in a continual, ecologically healthy way. And so it's this sponge and turning everything back into the sponge, nutrient cycling. And yet you in India, traditionally, in your natural farming, have demonstrated that, yes, we can sustain, perpetuate humanity, perpetuate economies, perpetuate social stability for centuries, millennia, through maintaining healthy biosystems. And see, it's really only in the last 100 years, or probably the last 70 years since the Second World War, where we as humans have said, hey, we think we're cleverer than nature, and we've left these natural processes behind and thought that we could actually do it better by adding oil-based energy and basically just accelerating then soil mining, effectively, oxidation of that carbon to grow bigger crops. And that was the basis of the Green Revolution, for example. And it's only now, after 70 years, that we're realizing, hey, that's not working. That's sort of oxidized our landscape. And so now we've got to actually revisit solutions beyond the Green Revolution. We've got to go beyond the Green Revolution and saying, okay, what are our options? Because the Green Revolution is leading to, in a sense, ecosystem and social collapse. And of course, India is very powerfully positioned because 60% of its community is still living on the land in villages. And so these natural farming revitalization strategies become enormously powerful, not just for India, but as blueprints globally for how we need to rebuild healthy ecosystems, healthy societies. And of course, what you've been doing in Andhra Pradesh, of course, is leading globally in that, not just in the natural farming, zero budget natural farming that you've been demonstrating, not just in the pre-monsoon dry seeding that you've been demonstrating to bring degraded land back into productivity, but also socially in terms of your women self-help group and the social village coordination organization to re-empower grassroots regeneration, farmer-based regeneration. So look, that's basically what we talked about in the how, right? Basically, yes, we have enormous crises globally. Yes, we have enormous challenges, urgent challenges. But when you look at what we need to do, and then you look at this third module of how, we say, yes, there is this natural solution, nature. All the answers are there. There's always more to know. There's almost more to learn. but we're only going to learn that by doing it, by observing it, and by discussing that in classes like these master classes, the very good questions you raised at the beginning. Okay, so that's in a sense what the objective, the purpose of module 3 was. But now very, very happy, Diksha, to take on board the agenda and answer the questions that have risen from that. As before, some of these questions are raising very, very important things that we'll be talking about in subsequent modules, but that's okay. But we'll still try to answer them, but we will refer back and say, look, we're going to be looking at some of these in much bigger detail later on, so that this isn't the last time we visit those topics. But look, over to you. Thank you very much. And I hope you've been enjoying this whole masterclass process and interaction as much as we have, Ben and Stephen and I here in Australia with the Regenerate Earth team. So excellent. So over to you.
Yes, Walter, definitely. We are also enjoying the masterclass session and we are learning new things as we are going forward and continuing these discussions after the masterclass ends also in the breakout session and in our respective WhatsApp group. Thank you for that wonderful recap. It did help in encapsulating module 3 for us. So the first question for the Q&A round, I'll read it. How do microbes help in the conservation of water and soil carbon when soil is covered with mulch during summers? Assuming that microbes release more carbon into the atmosphere in case of decomposition, microbes may follow some other pathways to conserve soil carbon during summer, such as formation of biofilms or biocapsule that retain carbon and moisture. How use of natural farming botanicals ensures more accessibility of nutrients rather than using bulky organic manures.
Right. Okay. Well, look, yes. Now, this is coming directly into module number 5, where we're talking about, the sponge and really rehydrating landscapes. You know, what are the processes whereby we can rehydrate landscapes to turn deserts back into green, productive landscapes. And it all comes, as the question validly asked, about microbes and plants. How does nature do it? Obviously through microbes and plants. And what is it that we can learn from that? Now, as we basically will be talking about in now module 4, so this is, again, people are very sharp, ahead of the game. It's basically by creating soil structure, by creating three-dimensional matrices in soils, allowing infiltration, retention, and then availability of water from that soils, that the microbes, by creating these structures, for the first time enables soils to store water. Prior to that, they couldn't. I'll just step aside for half a second and pull together, because we made this little prop that we'll be talking about in module 4. And what I've got here is I've got a little granddaughter and I bought her some toys, and these are just some little discs that can fuse together. They're just 10 little plastic discs. But when you see them, they're all bundled up. They might be, if you like, typical of a little rock, right? Whereby all these minerals are fused together. And as you see, it's quite a compact little rock. It's quite heavy for its volume. But if you look at the different colors, if you look at the red one, for example, there's a very limited area of red that's available for dissolution. And see, what microbes do, they'll take these same mineral particles, dissolve them, and then they'll put them together in new forms. And here I have the same 10 little discs, exactly the same as the other one, but they've just been fused together. And as you can see, they create a three-dimensional matrix, which is vastly more voluminous than the solid rock, right? So it may have 5 times the volume of this rock. And just the question with the water, just as if we put water on this rock, or this fused mineral particle, very little can infiltrate or very little can be retained. Whereas once we have an open matrix, then of course we can infiltrate and retain vast quantities of water in this three-dimensional space. And this is exactly what happens in soil. And what is the microbes are doing, they are simply sticking these particles together. I've pulled them apart now, but if we put them together as microbes do, they are creating these three-dimensional structures, which is then creating the sponge. Excuse me. So that's all the sponge is. It's actually just microbes rearranging mineral particles, adding organic matter between them, gluing them together to create these wonderful three-dimensional structures. Basically, microbes, the volume or the weight per volume of this thing, or the bulk density of this, is perhaps a third of what this rock is, right? If you weigh this, they weigh exactly the same, but this one has 3 to 5 times the volume, which means that, you know, up to 60% of the volume of this is made up of nothing. So by microbes bringing these things together, they're actually just adding nothing to the soil. But in doing nothing or adding nothing, they're vastly changing the functionality of this soil. In module number 6, we'll be talking about biofertilities. And again, we'll come back to this because you see now we've got these 2 red discs, whereas before very little of the red was available for absorption of nutrients. Now we've got vast increases in availability of nutrients on these red discs. And so we can again increase the biofertility of the soil, not by adding more, but simply making surfaces more available. And again, that's how nature increases biofertility. So basically, that's how nature creates water holding capacity in soils through microbes gluing together soil structures. And it's this simple, I mean, it's just this one simple demonstration happening all over the world for the last 420 million years. And as we said, nature just did this one simple thing once, and through that has fundamentally changed the hydrology, the biofertility, the rootability, the resilience, the productivity of these soils and the landscapes that we depend on for our future. So it's that simple. We'll go into it later on with pre-monsoon dry seeding. There's also other ways that microbes are actually enhancing the hydrology or creating actually water in soils, and that's through generating metabolic water. It's a process whereby, in a sense, microbes breaking down organic matter are turning that cellulose, that sugar, back into CO2 plus water. See, as we created biomass, as photosynthesis creates biomass, it takes CO2 and water from the air, and with solar energy fuses that into a sugar molecule. When microbes break that sugar molecule down, then it's releasing CO2, but it's also generating metabolic water, returning some of that water back. And that water is generated by the microbes in the soil. And that actually in arid conditions and in pre-monsoon dry seeding environments is the fundamental first process to enable plants to colonize and germinate in otherwise arid soils. So again, there's another process whereby microbes are not just making soils more water absorbent, but actually creating water for the growth of plants. But that's a particular case, and we'll talk about that later on when we're talking about pre-monsoon dry seeding. But so, yeah, microbes have a fundamental role in creating soils, creating hydrology, or enabling those soils to have hydrology. And of course, hydrology is life. Nothing on this planet lives without water. And of course, as we will also talk about, hydrology is 95% of the heat dynamics and governs 95% of the climate of the blue planet. So if we're going to cool the planet, again, we can only do that hydrologically through restoring some of these water-based cooling processes. So we'll talk about that as well. But look, wonderful question. And again, sorry for being so long in answering, but these are really profound, valuable questions that you're asking.
Thank you, Walter. That visual demonstration was very helpful. Second question is, what is the wheat's contribution in soil flora? Weeds removed from the soil as unwanted plants and nutrient competitions. Are there any changes occurring in microbial biodiversity by the removal of weeds?
Okay. This is, again, a very powerful question and very big discussion. We could have a masterclass just on weeds, but in a sense, we're starting that process now. There is no such thing in nature, of course, as a weed, right? A weed is simply a plant that we as humans think is inconvenient or we don't want where it is growing. Okay, so we're just deeming things to be unwanted or undesirable. And basically nature has put that plant there. Why? Because that plant has got a competitive advantage in growing in that site. Okay, so really plants will colonize whatever they can, all plants. And obviously where there's plants that are a bit more aggressive, more superior actually in colonizing, and they get sort of more populous and crowd out and dominate, we of course call them weeds. And why we call them weeds is because if we call them weeds, then industry can sell us weedicides, right? Basically, we are then told we must get rid of these plants. And of course, we are told we can get rid of them by poisoning these plants and then theoretically removing them. But of course, that doesn't happen. All that it does is bankrupts our bank balances and kills us because the weedicides are effectively highly dangerous poisons in themselves. But we can kill individual plants, but by doing so, all we've done is recreated a vacuum in that soil environment for that weed to actually recolonize and redominate. And so what you find is you're killing weeds, killing weeds, killing weeds, and all the time creating an environment which is conducive for more weeds to grow and dominate. So we are in an endless negative spiral of paying money for insecticides, for weedicides, biocides to kill them, in the process harming our health very, very seriously, but never actually achieving the endpoint that we want of removing this plant permanently. See, there's not one plant that we've actually removed through biocides, through weedicides on this planet. And there's, of course, no plant that has dominated and colonized the whole world. Okay? I mean, there's no such thing as a weed in nature, because if there was, it would have taken over the vegetation of the planet hundreds of millions of years ago, right? But it doesn't happen, because every plant, by growing, including a weed, creates soil conditions through its rhizosphere, through its soil microbes, through its organic matter inputs. It creates soil conditions that improve the soil and make it no longer competitive for that plant. So by improving the soil, it actually creates conditions that are no longer conducive for its long-term survival, and other plants then dominate. So most of the weeds that we put on lists to kill are in fact critically important pioneer plants, early site colonizing, very competitive, very aggressive plants, but critically important in nature in colonizing degraded desert virgin spaces. So in fact, weeds are the pioneer tools that we need to learn to manage for regreening wasteland and desert. Okay, and by killing them, we're just creating more and more wasteland, more and more desert. And of course, we're not going to green it. All we'll do is kill ourselves and bankrupt our businesses, our economies. Okay, so that's what weeds are, in a sense, about. And instead of fighting weeds, what we should be doing is accelerating their natural ecology, their natural soil forming benefits. So we accelerate the soil conditions so they are no longer conducive for that weed. Okay, we make that soil conditions better, so the weed can no longer compete. And we find that in natural farming. As we have more intercropping, more 365-day green cover cropping, sure, there'll be isolated weed plants still there, but they will no longer dominate anywhere near as much because they won't be able to compete in that healthier, more biodiverse soil that we're creating. So the weeds will be there, but they'll be there as companion plants without harming the yield. So, okay, again, as I said, we need a whole masterclass on weeds, perhaps, but these fundamental ecological principles of weeds and their role in soil regeneration and microbial soil structural changes are very profound, but always very, very beneficial. There's no weed that is in any way harming the soil. In fact, the opposite, weeds are helping in petagenesis, in developing soils and in developing more and more productive biosystem. It's just human minds and economic systems in the short term don't see them as beneficial. They can't understand the benefits they're creating in that way, but there's a lot of money they make by selling us poisons to remove them. I hope that, again, stimulates a lot of debate because it is quite a controversial subject, but there's no question about the scientific evidence. It can substantiate exactly what we've been talking about in every case globally.
Thank you, Walter. How is it that cow dung and cow urine, which has antifungal property used in seed pelletization, also help in proliferation and growth of fungal channels in the soil?
Right. Okay. These are excellent questions, right? Now, obviously, look, anything we put onto the soil can be beneficial at the right concentration, at the right amounts, at the right time. But if the same material we put on that soil, if it's in the wrong concentrations, in the wrong chemical forms, at the wrong time, then it can be detrimental. I mean, like everything is balanced and everything has the right amount. If we have too much food, we can die from overeating just as we can die from hunger. If we drink too much, the same thing goes. Everything is in balance. Now, cow dung and cow urine, yes, fresh cow dung and fresh urine in concentrated form can hurt plants and it can hurt microbes because it can be too acid or too toxic or too concentrated. And so again, in a natural farming system, this is really all buffered because that's why the soil carbon sponge, the buffering, the organic matter, the microbes very quickly take this high concentrated input and neutralize it and buffer it and dilute it so that it's turned from being a concentrated toxic amount and it's now buffered and diluted to be an optimal biofertilizer and biostimulant. So it's turned from being, in the fresh state, toxic, it's then turned into a very, very beneficial, as I said, a biofertilizer, but particularly a biostimulant. Now, biofertilizer is pretty easy to understand. Urine, feces, that contains a lot of nitrate, nitrogen, amino acids, and what have you, and ammonia. And that, of course, is nitrogen that is very essential and beneficial for the growth of plants, much more so than artificial nitrate fertilizer. And so urine, cow dung can be extremely valuable in helping then the productivity of biosystems at the right concentration, buffered through healthy soils. So as a biofertilizer, it's clear to see, obviously, all the food that we eat that food because it's got essential nutrients that the animal needs for its health. It's also excreting nutrients after it's done its digestion of that food, what it doesn't need. And so this dung is extremely valuable biofertilizer to return back to soils. So that's the biofertility side of it, but more profound and more beneficial, and what, in a sense, you and Andhra Pradesh have realized through your natural farming inocular, is the value of this urine and this cow dung with correct fermentation, correct treatment and dilution and buffering, and its value as a biostimulant. Okay, so it's not just acting as a nutrient, but even at very, very low concentrations, parts per million, it can act as a very beneficial microbial stimulant or switching on agent. Okay, so what happens is there's lots of fungi, bacteria, biota living in soil, and it's the activity of these fungi, these bacteria, that make that soil healthy, that solubilize nutrients, that do the nutrient cycling. So much of that fertility of the soil is about the microbial activity of that soil. And of course, this urine, dung, at the right concentration, acting as a biostimulant, can actually switch on and enhance these microbial activities in soil. And of course, you can do that uniquely because, yes, you can add fertilizer, but the fertilizer doesn't have this biostimulant effect. It's not just, of course, cattle and urine, feces from cattle and big animals. This is exactly how, for example, worms fertilize soils. Worms are growing, living in the soil, moving through the soil, eating organic matter and soil, and of course, excreting that organic matter and soil detritus, debris, in its casting and its leachates. And again, these worm castings, these leachates, extremely valuable as biostimulants, switching on the microbial activity of the soil. And of course, through that microbial higher activity, helping the fixation, the solubilization, the access, the uptake, and the cycling of nutrients. And in a sense, it's those 5 microbial processes that govern 80% of the biofertility of soil. It's not the amount of nutrients we're adding, it's actually the health of those microbial processes that govern biofertility. And so cattle dung, cattle urine, managed in the right way, is extremely valuable. And that's, again, what natural farming is perfect. Hello, I'm getting a question here of America. Next question, please.
I would request Achutan to ask the next question.
Good morning, Walter.
Good morning.
And it's an honor to be in this class. So my doubt was, let's say very general it might sound, but how the weeds, not the weeds, sorry, is there any specific plants that can actually contribute more to the soil than normal plants in terms of soil exudates, so that in a case we can create a boom or a explosion of growth in mycorrhizal population?
Okay, thank you. Yes, this is very important again. And obviously, yes, there are different plants, and different plants have different levels of root exudation, and again, stimulate different microorganisms. And as you mentioned, mycorrhizal fungi, which again, extremely important as one of those pioneer soil forming structures. Just to come back to the big picture, plants, of course, are taking CO2 and water and sunshine from the air, making sugars in their leaves. And basically 30 to 40% of those sugars produced by the plants are going through the roots and getting exuded out of the root systems to feed the microbial ecology that is so important in building soil structure and building biofertilities, right? So first of all plants are investing in fixing sugars, but also exuding sugars in their roots, but some do it better than others, right? And obviously, depending where you are, different plants are more suitable under specific conditions. So if you're in a very, for example, pre-monsoon dry seeding environment, an extremely harsh, dry, arid wasteland, and then you can say here are pioneer plants that are particularly advantageous in putting exudates into soil and helping to fix, basically make available or enhance microbial activity that can fix and make available better nutrients. And I'm thinking of, for example, classically in Australia, it's the legumes in our wild, in our natural environment, for example, the acacia seedlings. And again, they're exuding lots of exudates into the soil and stimulating microbial activity in the rhizosphere, but also stimulating nodule formation, rhizobia inoculation, and then that's fixing more nitrogen. So different plant species in different situations have that stimulatory role. Another group that's very, very important in this are, in fact, the onion family, right? Because these have got very thick roots. They really are essentially, they must be mycorrhizal. You know, they can't really compete without being mycorrhizal, but they are actually, again, producing prodigious quantities of exudates, most of which are going to their mycorrhizae, and then their mycorrhizae are extremely valuable in primary site colonizing situations. And you can see that in nature, for example, where you've got lots of the bulbs, you know, the tulips and the spring bulb plants, onions, garlic, leeks, and so forth. And they're all colonizing primary soils, often early in springtime, because of their active mycorrhizal colonization, because of their high exudate production. So yes, converse also happens. Some plants are giving off exudates that can be phytotoxic. Okay, so they chemically are basically they're, well, how shall I say, they're antagonistic, or they prevent the competitive growth of other roots. And so you'll have plants that then dominate their site for that period of time through providing basically phytotoxic exudate leachates. And we call that allelopathy, right? Where basically plants will exclude other plants from growing because of their phenolic exudates or their toxic exudates. So basically, exudates become part of that complex soil microbial ecology, both stimulating microbes, helping that plant to compete for nutrients, but also, as we've said, with the phytotoxic exudates, allelopathy, preventing other roots from growing there. And so what we do with natural farming, we of course know what plants are compatible as positive companion plants. And by having them and having compatible plants, we can get 150% productivity because they synergistically help each other. But there's other plant combinations that don't work. because they can be phytotoxic for each other. So that's where the skills or local knowledge of natural farming comes in, and it's these multi-species cover crop, multi-species mixed cropping systems that then optimize overall productivities. So again, a very interesting, very complex, but very powerful field for us to understand better in natural farming, because it's through understanding that we can actually enhance the resilience and the productivity of our crops through these microbial soil processes. Thank you very much. Next question.
I would request Satish to ask the next question.
Yeah, sure, Diksha. Thanks. Hello, Dr. Walter. My question is on the nutrient availability. Thanks for the visual representation today. I think that was more helpful in understanding the bioavailability. So during the pathogenesis process, when the larger parts are broken down by fungi and mycorrhizae, so the bioavailability of nutrient increases and plants can take that. So my question is that there would definitely also be a finite concentration of minerals, right, in the soil or in the rocky formations. So how does this nutrient recycling takes place? Because anyway, farming in India has been for many thousand years. So I presume there is some kind of nutrient recycling going on. So I would also like to know.
Okay, well, look, I hope I can answer all the different elements of that, but we can explore it further in further questions, and of course, again, in module 6 when we're talking about fertility. Look, it's very simple and very clear. It must be so, mustn't it? Because as we say, here's Asia, India, China, and they've sustained highly productive, large populations of hundreds of millions of people for thousands of years on the same soils. And often those soils are initially not that productive, right? So it's nothing magical about the soils. Often it's a case of just their wise, sustained management of those soils. And why and how that happens is because, yeah, these soils are being continually recharged with nutrients from waste, and those nutrients are being then recycled and made available again for more and more productivity. So in nature, definitely there's so many mineral nutrients in the soil. We saw that in this little diagram or this little model we've got. Yes, there's nutrients in the soil, but those nutrients are finite, right? And sure, we can make more available by increasing, here we are, by increasing the surface area. But the point is they are finite. And so we can't continually mine and extract nutrients from soils. We've got to add them back in the long run. Now, we can, by increasing the microbial activity, make them more available. We can extend the amount of productivity we can get from every soil by improving this availability. But at the end, we can't mine and export nutrients from them. We've got to return them. And what natural farming cultures all over the planet have done successfully is actually return their waste, their dung, their excreta, their compost, and that of animals back to the soil, and then reincorporated that to get nutrient cycling happening, right? And that's, in a sense, been the basis of productivity. Now, obviously, again, it's microbes that are critical, because it's the microbes that are critical in breaking down this excreta, this organic waste, the compost, and releasing these nutrients and making them available again. So these healthy natural farming systems have a continual cycle of nutrients. What, in a sense, is powerful, and where India, again, has an enormous advantage, you've still got so many of your people living in villages or distributed throughout the countryside. So in a sense, they're in a perfect position to recycle their waste back onto the soils in very efficient, closed local cycles. It's much, much more harder in some of our industrial Western societies where we basically are mining soils for food. We're exporting that food, processing that food, and concentrating people in cities. And of course, all that nutrient is now in cities and the waste of cities, but that's far removed from the agricultural land where it needs to be returned to. And so what happens, you end up with toxic pollution, eutrophication of city environments because of the excessive nutrients, because it becomes effectively so concentrated and toxic, and you end up with both pollution, but often pandemic diseases because of the poor management of the waste. And in a sense, that's where 21st century, we have to come back to building these cyclic ecosystems, these cyclic economies, these localized, autonomous, distributive, cyclic ecosystems. And of course, the village is a classic optimum scale and model for doing that. Just think, if we have a city of 10 million people or 20 million people, how do we harvest and capture all their waste and turn it back onto their original landscapes from where those nutrients comes? It becomes a massive logistics problem. Whereas in a sense, we can avoid that problem totally at a village level. So yes, microbes are the critical organisms in this cycling. We've got to redesign and rebuild these nutrient cycling processes. As I said, with any addition, fertilizer, initially those wastes are often too concentrated, too toxic. They can also, in industrial settings, have a lot of heavy metals and other toxic elements in them, which create problems for breaking down or neutralizing. But the point is, we've got to design very rapidly biosystems, cyclic biosystems that work as in nature in this recycling process. And of course, the microbial ecology of waste management is really at the frontier of trying to do that. So I hope that helps answer part of your question, but I'm sure there may be other questions we can follow up in further on discussions. Next question, please.
Thank you, Walter. Next will be the last question. Uday, can you ask the question?
Yes, Diksha. Good morning, Walter, Dr. Walter. My question is simple. Our human anthropogenic activities damage severely environment so far. Can it regain with natural farming alone? Like partially or fully? My assumption is whole world will practice natural farming. Can we regain it? If it's not, how much probability?
Okay, look, I'm not sure if I
system
understood everything about the question. So could you just repeat it again, please?
Human activities damage environment so far, damage severely so far now. So far, how much regain it? And environment, healthy environment by natural farming. Is it possible alone by natural farming or regenerative farming or organic farming for sustainable agricultural practices? At what extent it will possible? What other systems need to parallel working with our natural farming practices? Parallelly or directly or indirectly?
Yeah. Okay. Well, look, thank you. And I think I understand. And the question is, of course, yes, having had this impact, the severe impact, how much can we achieve by natural farming to regenerate it? The first answer to the question is, well, look, there is no other process on this planet known to science that can otherwise fix it, right? So it's as simple as that. Like, the fact is that from all our knowledge of science, soil, pedogenesis, this is how nature creates soils, how nature repairs soils, and there's no other process that is known to science or nature to do it. So in a sense, yes, we've got this one method for doing it. But the good news is we can do this in most cases extremely rapidly and very, very profitably. So, for example, within years, like within a matter of years, by putting organic matter into the soil, by rebuilding soil structures, rebuilding its water holding capacity, its biofertility, we can start buffering and making soils more productive. We can accelerate that processes by wise natural farming practices, multi-species cover crop, successional plantings, integrating animals. I'll give you some examples. For example, the Dutch. The Dutch have got very, very little land. Most of their land is below sea level, right? And it's going to get harder as sea level rises. And the Dutch take toxic saline sludge from the bottom of the Rhine River, containing all those nutrients and toxins from Switzerland and Germany that are going down the Rhine. And they'll take this toxic saline sludge and through an accelerated natural farming pedogenesis process that we've talked about, within 10 years, turn that sludge into, of course, what we call polder soils or wetland soils through accelerated plant successions, right? They make these polder soils and then, of course, start growing their tulips and their flowers. And then from tulips and flowers very rapidly into productive agricultural soils. The tulips and the flowers, of course, as we talked about, are often these highly mycorrhizal plants that are very important in stimulating this process. But the point is that they, within 10 years, are able to turn toxic sludge with all these limitations and turn it into very, very productive soils for growing flowers and then vegetables. The Dutch are now the second highest income earner globally in terms of food export production. Okay, not that they are the most highest volume of food production, but in terms of value. So effectively without land, with minimal land, but a very, very astute, wise pedogenesis soil regeneration strategy on very limited land, they're now the second most valuable food producer. So yes, there's an example of how people can do it. We've got the same example, of course, in India with your farmers, your natural farming community leaders, where they're again going into all sorts of different environments. And as Vijay, as Andhra Pradesh is showing, getting 200% of the yields, often 3 crops instead of 1, 365-day green cover, and actually producing higher valuable, higher yielding crops with 10% or less of the inputs. Again, within years, by simply these soil regeneration processes. We've got the same story, of course, with pre-monsoon dry seeding, where so far humans have created 5 billion hectares of man-made desert and wasteland on this planet, some 40% of the land area. But here, through pre-monsoon dry seeding, we're able to get plants colonizing some of these otherwise arid wastelands and getting plants started, and again, slowly building back and potentially regreening, rehydrating what would otherwise be arid, dry, red wastelands. So India's, Andhra Pradesh's experience of turning, soils that are red, brown, desiccating for 70% of the time and turning them to 365-day green plant covers, again, are demonstrating we can do this. But look, yes, here are the innovators. They're showing they can do it. Here's nature that shows us it can do it. But we've got a major challenge because these are the innovative leaders. We've got to now, through this masterclass and initiatives like this, extend the knowledge, extend the practices, extend the realization that this is the only way we can actually secure our future water, food, biosystems, and social needs. So yes, it can be done, but there's still a long journey ahead in extending that. And of course, you as the masterclass and you as the catalyst, the leaders in education and extending this are critically important in that. And of course, in this masterclass, we'll just keep on working on the further modules, looking at, what are the techniques and processes and benefits that we can realize. So collectively, we can make a compelling case for the power and the value of natural farming as the only way we can restore a healthy future for humanity on this planet. But look, I mean, obviously, yes, we're getting close to time. So if nothing else, let's close it there. And then what we'll do is we'll send the next module, module number 4 now, which is really all about getting into the details of rebuilding the Earth's soil carbon sponge, but also the practical approaches for doing that. Just as the last question was asking, okay, how do we actually physically, practically do this everywhere at the local grassroots level? Regenerating the Earth's soil carbon sponge, because as we learned in this module, that's the only process that is available in nature and in science for regenerating landscapes, regenerating the Earth. Over to you.
Thank you, Walter. We have received the module 4. We will be sending it to the participants shortly after this call ends. Dharmendra sir, I would like to request some closing remarks from you and tell about the breakout session as well.
Yeah, first of all, big thanks to Walter for an excellent recap, and also explaining how each process is important in natural farming. So these questions are coming from us after some study only. So even after some hours of study, if they are still unable to get some points, so at that stage we are collecting these questions, and that's why we are also encouraged by the kind of questions participants are asking. And thanks for answering them excellently well as well, Walter. And I think we had an excellent 1-hour session. So we look forward to go through the next module, that is module 4. And we'll be having a pre-work session, not tomorrow, but on Wednesday. So I request all the participants to go through the module in advance and come prepared for a rich discussion. Okay. So with this, I think we'll close the Q&A session. And we are not done yet for this. We'll go out into some group work where we'll try to summarize what module 3 is about. We have 6 subgroups, and each group will be one topic will be worked out by 2 groups. So we'll get summaries of as a part of group learning, all of that. So next 30 to 45 minutes we'll spend in that exercise. And now this Q&A session ends, and thank you so much for your time, Walter and Ben and Stephen.
Yeah, thank you very much. And look, none of these questions are lost, because as we record them all, and at the end, we'll really have a very powerful list of critical questions, because that really is going to do so much to say, look, these are the future critical areas for natural farming moving forward. So thank you very much, and look forward to seeing you again next week. All the very best. Okay, bye-bye.
I have posted the link for breakout room sessions in the WhatsApp group. Please kindly join.
So that will be another account.
Yes, sir. Yes, sir. We have to close this now.
In the chat here or in the WhatsApp? Okay.
In the WhatsApp, sir.
WhatsApp. Okay.